Hello, everyone. This is our eighth week, and in this week we are going to talk about mainly two topics. The first one is multi-stage experiments, which is different from previously discussed the single-stage experiments. And the second topic we're going to discuss is very important. It is called a conditional probability. So we have in the previous lecture we have already defined the stochastic independence between two and more events, and this is um, remember, if you can calculate like the P times PB is equal to PA intersection with B, and that we can find out whether the two events are stochastically independent or not. And but here, let's discuss some more advanced situations. For example, if there's a chain of event, for example, you first must pass a test to enter some association of sports, and then you want to send your team into a final stage, and then win the champion of that association. So this is a chain of event, and every event has a probability if you can do it or cannot do it. And in this case, we are discussing whether each of these events are physically independent or if they are physically dependent. And we can use our previously discussed stochastic independence to reveal its physical independent qualities. So let's first see one example. So if we roll dice twice and consider events of A is the first row is a 3 and B is the second row is even, and we can calculate the PA is equal to 1/6 and PB is equal to 1/2. However, once we want to find out if A and B are independent or not, we must calculate if they're their intersection. Both of those two events happen and their multiplication. So first of all, we will discuss like the first row and the second row. There's two stages experiment. So we will form a sample space with W1 and W2. So in the A case is that the W1 is must equal to 3 and W2 can be anything. So it's definitely totally two different cases. And if we calculate this out, it is a 6 divided by 36, which is the cardinality of the sample space. So it is 1/6. But however, if we consider B, in B case, like W1 is not limited. I mean, W1 can be any case, but W2, the second row is even. So there's only three cases, 2, 4, and 6. So in this case, the cardinality of the B event is 3 times 6 equal to 18, and the 6 is the W1 term, and 3 is the W2 term. However, when we deal with like A intersection of B, so first row it was a 3 and the second row is even. So both of the two cases are limited, and in this case the first and in this case the first must be 3, and the second row must be 2, 4, and 6. So there's only 3 possible cases, and then we can find out like the PA is 1/6, PB is 1/2, is 18 divided by 36, and PA intersection with B is 3 divided by 36 is 1/12. So are they stochastically independent? We just need to time these two terms together. So it's 1/6 times 1/2 is 1/12, which is the same as A intersection with B, the probability A intersection with B. So we already proved it is yes, they are stochastic independent. So in this case, we'll reflect the previous experiment that the two events are physically independent. So based on the stochastic independent we have proved here, and we are able to figure out they are physically independent too. So we always use mathematical term to find out stochastic independence, and then we can conclude it's more real case. It's more real case that they're actually physically independent. And the first and here we want to introduce a new concept. It's called the product space. Hopefully you already understand what's the Cartesian product. So let omega a fancy A and a P, this probability triplet with an index I, with discrete probability space with Pi, characterized by the probability mass function Pi, which sends each sample space to 0 and 1 interval. And the discrete probability space with sample space is this one. It's an n tuple with each outcome W1 to Wn inside it. And the product measure P can be defined as just time them together. So this is our definition. But ask yourself, why is that? Why is that the case? So we'll find out they're actually it's the case. First of all, because you have like n different stages of events. So the first outcome, second outcome, the last outcome, they're mutually not independent, but they are not related to each other. So we just list them one by one here. But if you want to find out why this is true, it's the simplest method to consider is that because W1 times W2 times so many terms until like Wn. If we can time these terms together, and we definitely will find out that if this is same to say that W1 happens, W2 happens, and Wn happens. So if they are independently related to each other, and we just times those probability one by one, as the last lecture suggested, the formula we have already finds out. So let's give a more like more thought on this one. So let probability triple exist, and because this is a Laplace experiment, so the cardinality of the sample space must be finite, and the probability of each of this outcome is 1 over the cardinality of sample space. And this is what we already this is the assumption for this question. So suppose we repeat this experiment n times. So repeat this n times. So here we have n terms inside this tuple. So suppose we repeat this experiment n times, and the sample space will be n times together. This is by the definition of Cartesian product. So the sample space, the cardinality of sample space here is might be the omega's sample space to the power of n. And also we'll find out the probability of each of the outcome occurs. And this is also because the cardinality increases to the power of n, and there's only one outcome for each outcome, and this is 1 divided by omega's cardinality to the power of n, and this is what it tells us. And we want to introduce another important definition here. So we want to introduce each event. It is an outcome of the ith experiments is in AI. Then it can be written as AI as the omega belongs to if the omega belongs to the if the W belongs to omega, then the WI belongs to AI. So what does this mean? It means that it just means that the AI with the I don't know how to pronounce this one, but we define it as the AI, strange AI. The strange AI, it means the ith term of the W is belong to AI. So it doesn't consider all of the case of other events except for AI. It's just we just consider AI, but the outcome of the ith term must belong to AI. And and we found out that that AI belongs to is a subset of omega I, and strange AI if the strange AI is defined as here, then P strange AI is equal to PI AI. So why this is the case? Because we're only consider AI. We're not consider AJ, AK, or AM, other A. So all of the other probability are one, and this is the probability that is not one. And if we time out 1 times this term, it figure out to be this term. And now we can say all of the events like the strange A1, strange A2 to the strange AN are stochastically independent. And this is an example to illustrate this. So the P strange AI is equal to the sum of all the possible cases that is belong to AI, a strange AI, and the PW. So this is the definition of how we find out the probability. And because we can, all of the WI are belong to AI, we can time these terms out. And because of like for each of this sigma, this summation of W1, W2, W3 to Wn, all of these terms are like they have different Wi. They have W1, W2 to Wn. So we can separate them out into different summations, and then time them together. This will not change the value of the original formula. So we can times omega 1, omega 2, omega 3, omega to the omega n. We can separate those events out, and because of like all of the W1 is belong to omega 1, W2 is belong to omega 2, but only the Wi is belong to AI. So because we discussed many weeks before, like if one for each of the discrete sample space, if like omega 1 is the case for all of the outcome, this is equal to 1. This is the case that all possible happen. So this is 1, and all of the terms are 1, and except for this one, it's not 1. This is exactly what we define here is the PIAI. So the final term becomes PIAI. And we also want to find out why those a strange A1, strange A2, strange AN are stochastically independent. And here we'd like to say it is independent. And if we just want to find out how to prove an independent case, we just need to prove out if the intersection of all of this event is equal to the multiplication of those simple terms probability. And so we just want to say for any indices 1 smaller than I1 smaller than IK smaller than n. So this means like we are picking randomly selected index between 1 and n, not from 1 to n, but like any combinations and the selections of the index from 1 to n. And as we like calculate them together, we find out, well, this is because we intersection with them all together. So this is I1 is belong to AI, WIK is belong to AIK is all in this situation. So we can make one step more clear is to separate all of the summation for each of these cases. So we as we illustrated above, like here, we separate the summation like W1, WI belong to AI, and separate all of those terms out, and this is So why this is the case? Because imagine like if we sum up from we are only consider the index wi1, but so we just sum up all of the wi1 term here. We are not considering any wi2 terms, and wi2 terms are considered in the next summation. And we sum of them together and times them together. This is the law of the distribution. Will not in fact will give us the equal outcome. And for each of these terms, they are just pi1 ai1 pik aik. So all of these terms are explainable by a simplification, because this is the definition of the discrete probability measure. And as we find out, the conclusion here is the PAI, strange strange AI is equal to PIAI, and the strange and the PIAI can be written as P strange AI. And we find out like exactly the multiplication of these strange probabilities are the intersection of these strange events. So we'll prove that they are stochastically independent and physically independent as well. And let's see one more example. A machine tosses 5 coins at random, and the coins are mutually independent, and each coin has like p hat is equal to 1 minus p, p tail is 0.1. So the probability that tail that gives us a head is 0.1 and give us a tail is 0.9. So what the probability that exactly one coin shows? What's the probability that exactly one coin shows heads? So there are 5 possible outcomes. Comprises exactly one head. That is because we have 5 coins. The first coin, second coin, and each of the coin can be a head, and that's the only case exactly one coin shows head. So by independence, because all of the coins are mutually independent as the assumption of this question. So each of these events has probability 0.1 times 0.9 to the power of 4, because there are 4 cases which shows tail and 1 case shows head. So exactly one coin shows heads is 0.1 times 0.9 to the power of 4 and multiply by the 5 for the 5 possible outcome. And this gives us roughly about 32.88, 81%. And so there's one more question to ask. It's like which end maximize your probability for winning the game. Like you want to if you toss n coins and there's only one head and you wins the game, and there's more. If there's not exactly one coin shows head, you lose the game. So what n maximize the winning chance? So we can just use the n to denote how many coins are there. So exactly one coin shows heads is n times 0.1 times 0.9 n minus 1, as we illustrated here. The same logical sequence consideration as here. And we find out it's n times 0.1 times 0.9 to the power n minus 1. Okay. And we want to maximize this term. And how to maximize it? How to maximize this term is let me see. So because there's for every increases of n, the proportion of n increases must be greater than 0.9. Like 0.9 is like 10%. If that's greater than 10%, we increase its chance for winning. But if it's smaller than the 10% as 0.9, we are decreasing the total probability as this formula gives us. So if we move from 8 to 9, the 8 divided by 9 or 9 divided 8 is greater than 1.1. So we are still increases. And 10 divided by 9 is just the same as 1.1. So we are keeping the same, but 11 divided by 10 is smaller than 1.1, which is smaller than 10% increase. But here we decrease by 10%. So we are lose the chance. So we'll say like if n equal to 9 and n equal to 10, that's the maximizes cases, which is around like 38.74%. And now we are moving to our second topic, the conditional probability. So let's give a very easy case. It's like if you know a person that's born in the street that is born in April, you don't know whether it's born in April or born in any conditions. So the probability that a person born in April is 1/12, because 1 year have 12 months and each month have the same probability that one person can be birthed. But once you know, as you like chat with that person, know that he's born in spring. So now the probability that he born in April becomes 1/3, because the probability of born in April given by his born in spring is 1/3. So this is the simple case considered as conditional probability, as we have a condition here, born in spring and born in April, probability changes. So let's give a more rigorous definition of conditional probability. It's like if let A and B belongs to a sample space are events that P, at least the probability of A is greater than 0, or if it's equal to 0, we cannot calculate this term here. The denominator cannot be equal to 0. So the conditional probability of B given A is defined as this one, is A intersection of B divided by probability of A. And this is exactly like to change the sample space from omega to A. And this is the condition on A, because we already know we can know A happens and we can limit our consideration, the possibility of outcomes into A instead of the original sample space. And why this is true? So the probability of B given A is equal to A is equal to this one, and this is equal to A intersection with B divided by the cardinality of A. And if A and B are independent, we know that these two terms can be written as B minus B divided by sample space, because if they are independent, and now this is just equal to probability of B. So if A and B are independent, then this is a if and only if case. So if A and B are independent, then the probability of B condition on A is equal to probability of B. So one question might arises is why they're independent, and this can be true. This can be true because the independence tells us that this can be written as B, how to say, like B times A. So B times A, if B times A is the case, and B, this becomes cardinality of B times cardinality of A, and A is divided out and only B remains. So it's cardinality of B divided by the the cardinality of sample space. So this is probability of B remains. You can say there's A divided by omega, and there's if you separate those terms out as cardinality of A times cardinality of B and divided by, there will be two omega, cardinality of omega, and there will still remains one in the bottom. So this is the case. And so let's use the Venn diagram to illustrate this case. As so suppose the omega is all of the undergraduate in University of Washington, and S is the student taking stat 394. A is the student athlete. So there are three sets here, and we already know that there are 43,000 students in UW and 116 students in our class, and 741 students are athletes. So and we ask like how many students are athlete in our class. There's 2. So the intersection of athlete and student taken 394 is 2. So let's consider several cases. So what is the probability of A given by the condition S? So what is the probability that if we already know a student is in the class 394, and what's the probability of that he is an athlete? This is given by the intersection of A and S divided by the cardinality of S, which is 2/116. But what is the condition that if we already know a student is an athlete, that he is taken 394? So this becomes A intersection with S divided by A, because athlete is our condition right now. We already know it's athlete. So this is 2 divided by 741. So maybe it's a surprise that the probability that we know one student is an athlete, and that he's taken 394 has a lower probability than if we already know he's taken 394 and given by his athlete. So possibly like most athletes, it is more common that athletes want to take 394. So maybe this is a conclusion we can draw from, but I'm not pretty sure, because there's far more variables we should consider. And now we want to give a rigorous treatment of the birthday problem. Like you randomly choose a person on the street, and what's the probability that the person is born in April, given by his already know that he is born in spring. So we will use 3 different sets. So B is April. B is April, which means B is his birthday month. And at spring equal to March, April, and May. But by my sense, like the spring is not. It would be these 3 months is equal to February, March, and April. And the omega is 12 months. So the probability of a B intersection with S is like intersection with these 2 sets and give us April, which is still like the B. So it's 1/12. And the PS is equal to 1/4, and the B condition on S is equal to B intersection with S divided by PS. It's 1/12 divided by 1/4 is 1/3. We sub this one. And there's another example. We draw 2 times without replacement from the urn with R red balls and N-R white balls. So this is an urn with N balls, and R of them are red balls. So there's 2 cases we want to consider here. The first case is A is equal to first ball is red, and B is second ball is red. So the question we want to ask is, what is the probability of like the second ball is red given by the first ball is red? So first of all, we'll calculate the term PA. PA is equal to R minus N, because this is a type 2 model. There is a sequence, which means the sequence is considered first ball, second ball, and it is drawn without replacement. So this is definitely a type 2 error model. So PA is equal to cardinality of A divided by cardinality of omega, which is R divided R over N. And what is the probability of A intersection with B? And this means like you first ball is a red ball, and second ball at the same time is a red ball. So this is given by, this is the case that R over N times R minus 1 over N minus 1, because at the second draw you already lose 1 ball, 1 red ball, and the urn loses 1 ball in total. So it's R minus 1 divided by N minus 1. So in this case, it's the probability of B given by A becomes becomes the probability of A intersections B divided by probability of A, which is equal to R minus 1 divided by N minus 1. And we solved this one. And there's a very interesting formula I want to introduce is if A1, A2 to AN are events with probability A1 intersection, which means all of this intersection is 0, then I don't think this is really important. So they are just events. They're just events from A1 to AN. And the probability of A1 intersection of all of this intersection of these events is equal to probability of A1 times probability of A2 given by A1 and times and for each terms there's a new A something given by all of the A something previously. So why it's true? Because the right hand side is equal to this term, and PA1 is PA1, PA2 given by PA1 is PA1 intersection with A2 given by PA1, and if we can write out all of these terms out, and we find out we can actually cancel each term one by one, and the last remaining thing is the last term, like A1 intersection to AN, which is just the right hand side. So we done the proof, and this is a really important formula that we can use in many questions later, and we'll see them as we encounter. And I want to introduce the law of total probability. This is central in the like the introduction to probability course. Law of total probability, which means so this formula can be very hard to understand, but just think about this graph, like B1, B2, B3, one sample space are divided into n different separate sets, and A here, and A is event, and it is in several of the cases. And if you want to find a PA, we just sum up like all of the B1 intersection with A, B2 intersection with A, B3 intersection with A, and we time them all together, and we get a PA. So this is the understanding of this law of total probability, and why we are saying like A intersection with BI. And the formula here is not A intersection with BI, because if we time this term out, it is just A intersection with BI, because we can look at the term here. A intersection with B is this term timed together, which is just this term. So this is the law of total probability, and we want to see some cases that some real examples that illustrate this point well. So the first example is drawing lottery tickets. A box containing 10 tickets, and 3 of them are winning tickets. 7 of them are losing tickets, and pick 3 at random without replacement. So I would say like this is first, the order is the order considering. Yes, because we're asking like what the chance that the first 3 randomly picked tickets are the winning ones. So the order is considered, and because it's without replacement, this is a like the type 2 EARN model. So let's answer the first question. So what is the chance that the first 3 randomly picked tickets are the winning ones? This gives us like P W1 intersection with W2 intersection with W3. So WI we define is the ice draw is the winning ticket. And we can use the formula here. As I said, the multiplication rule. This is very important. So we want to find the intersection with these 3 events. So the first is P W1 times P W2 given by W1, and the P W3 given by W1 in the second is W2. Okay, and what's the probability of W1? This is 3/10 because there are 3 winning tickets. And for this term, given by the first one is a winning ticket, what's about the second tickets? Because we lose 1 winning tickets and 1 tickets in total, so there's 2 divided by 9. And what is the probability that the third draw is a winning ticket given by the first 2 draws are winning tickets? This is 1/8 because there's 2 winning tickets loses, so only 1 remains. And this, if we calculate this out, is equal to 1/120. So the second question asks, like, what's the probability that the second ticket is a winning one? Okay, this seems like a hard question to answer because we are escaping the case. We don't know whether the first ticket is a winning one or not. So this time we will use the law of total probability, like the PW2 happens is equal to PW2 intersection with. So we can separate the first case into 2 cases, like whether the first lottery is a winning one or it's not a winning one. So we use a union to link W1 and W1's complement. And once we can figure out this term, we use the probability of like W2 intersection with W1 and this is and from this step to the first step to the second step, we use the law of distribution, and we can find out it gradually turns into W2 intersection with W1 plus W2 intersection with W1 complement. This is we use in the law the total probability law. And by using this Venn diagram, we can see we just separate the W2 into this term and this term. So we just combine them together and we find out the W2 as a result. So W2 intersection with W1 is P W1 times P W2 given by W1 plus P W1 complement times P W2 given by W1 complement, and this is 3/10 times 2/9 plus 7 divided by 10 times 3 divided by 9, and we give 3 divided by 10 as a result. So so luckily, because we find out the first ticket is a winning ticket is 3/10, and the second winning ticket is winning ticket is also 3 divided by 10. So maybe no matter how many tickets are there, no matter what number we are choosing, all of those tickets are winning tickets. They have the same probability. So imagine there's 1 million tickets and 100 of them are winning tickets. And no matter what we are choosing from, maybe 1,000 of them are winning tickets. So no matter which tickets we're saying, like the first tickets are winning tickets, the second tickets are winning tickets, all of those probability are equal to 1/1000. So let's look closer to why this is correct. This is because W1 times W1 PW1 is 3/10, of course, and PW1 complement is 7/10. But as we say here, we already solved like if the first winning ticket is strong already, then the second winning ticket is 2 or 9. But here is a case that dependent by the first tickets is not winning ticket. So still 3 tickets remains, but only 9 tickets. 3 winning tickets remain, but only 9 tickets remain. So it's 3/9. And additional example another example is the birthday problem. So what's the probability of like two people, Ali and Bet, have different birthday? The probability that they have different birthday is like Ali not equal to Bet is 364 divided by 365. This is because let's say Ali is the first person. He can have birthday on any date. So there's a probability of 1 that he can have a birthday. But for Bet, he cannot be the same probability as Ali. So his birthday must be any of the date except for Ali's birthday. So it's 364 divided by 365. And if we also consider person C, the cow, so different birthday for all of them, we can use the conditional probability here. And because cow cannot equal to Ali and cow cannot equal to Bet, so this is the case that this is the case that he can only be 363 days except for the Alice birthday and Bet's birthday. And then we join another person, Dan. So we have person A, B, C, D. We have 4 people right now, and this is the conditional probability we'll use in the last example as here, given by this case. I already know that the probability of all of those births that are different are this term. I'm just consider D cannot equal to A, D cannot equal to B, and D cannot equal to C. It's 362 divided by 365, and we are done. And here's another rule called Bayes' rule. And for the same reason, Bayes' rule can be the first glimpse of the formula can be difficult to illustrate, but we can see examples to explain Bayes' rule. Bayes' rule, from the first understanding, it's just like if we can calculate the probability of a certain event A, we can know it's A, and then we can find out what's the like a subset of B given by A by using probability of A as a denominator. And we can see one example. This is an example of testing for rare disease. So lab tests produce positive and negative results, and 95% of the case that the test to correctly identify a sick person that is being sick, and it's 98% the test to test correctly identify a health person as being healthy. So what is the probability that the lab test is positive from a random person? Okay, so in this case, we use the law of total probability, that the probability of positive is equal to sick case times positive given by sick, and not sick times probability that positive given by not sick. And this is equal to 0.01, the sicking probability, and times the probability that the sick person identified as positive is 0.01 times 0.95, and the person that is not sick times the probability that a not sick person is not sick. This is 0.99, the population given by the probability 0.02, and this is equal to 2.93%. Okay, so this is just using the law of total probability, and now we want to find out the suppose the lab test of randomly select person is positive. So what is the probability that the person really has the disease? So he's not kidding; he really has the disease. So this is the same case that we want to know. If we see one person is test positive, so what's the probability that he's really sick? And this is a new condition. We already know is positive. This is sick given by the condition positive, which is equal to probability of sick intersection with positive divided by probability of positive. And then we use the Bayes' law here. So the Bayes' law says the probability of positive is what we discussed here. We use the law of total probability, the expansion of the formula as its denominator, and we use the probability of sig times positive given by sig as our numerator. So what does this mean? So we already calculated this term before. Positive given sig times probability sig. This is exactly positive and sig at the same time. It's 0.01 times 0.95, and the denominator is 2.93. So this result will be less than 33%. So I think this example illustrates the law of the Bayes law wonderfully, the Bayes rule. Yeah, the Bayes rule. So if we want to find out some subset given by a condition, we're just using a law of total probability to calculate the probability of that condition as a denominator. And we want to use, and then we can just use the, so especially we know this probability and this probability. So we just separate the subset in the denominator out as a numerator to calculate its probability. So usually for such questions, for such conditional probability question, we can draw a tree to illustrate it. And we can separate, so in this question, we can separate the population into sick population and non-sick population. And sick population given by positive is 0.95, and non-sick population given by non-positive negative is 0.98. And in this condition, we want to find if a person is positive. Given by a person is positive, we'll find whether it's sick. We just sum out these two branch, 0.01 times 0.95, and this branch 0.99 times 0.02. And we sum out these two branch as our denominator and use this term as our numerator, which is very, very easy to understand compared to this formula above. But this formula is just saying the same, just telling the same story as we illustrated below, which is just say like sum up all the possible cases for A, and for the certain term BK, we just move the probability of A given by BK times probability BK out to be the numerator, and we are done. So let's use one additional example. The example is the same. It's still like the testing. It's still the real disease testing. But now we want to find out what's the probability that given by the test is negative. What's the probability of the person do not have the disease? So this is equal to say not sick given by negative. And first of all, we want to calculate all of the negative case as in the denominator, and we will pick out the negative case given by not sick. So this entire term as our numerator. I found out, okay, 0.01 times 0.05 plus 0.99 times 0.98. This is very close to 1, so it's definitely greater than 99%. And if we want to ask about what's the probability that given by the test is negative, the person have the disease. So these two questions are complement with each other. So we just use 1 minus, one minus this probability, we can figure out this one. But another way to do is to replace not sick given by is to replace the not sick subset with the sick subset. So 0.99 times 0.98 is replaced by 0.01 times 0.05. So the result will be 0.052%. And the last example I want to see is another multi-stage urn model. So there's 6 urns and 5 bowls in each urn. And the first urn has 0 red bowls. The second urn has 1 red bowl. The third urn has 2 red bowls, and the last urn has all red bowls, which are 5 red bowls. And so the multi-stage experiment goes like this. The first stage, you roll a die and select one of the 6 urns, and at the second stage, you draw a bowl with replacement from the urn. So this is a type 1 urn model because replace with replacement and the order is considered. So BI is equal to the bowls are drawn from the ith urn, and A1 is the first bowl is red, A2 is the second bowl is red. So there's 2 questions we asked. The first one is how to compute the probability of A2 given by A1. So in this case, A2 given by A1. So first we want to calculate what's the probability of A1. What's the probability of A1 is difficult because in each of the different urns, they have different number of red balls. So A1 is also a conditional probability. That is a condition on BI. So first of all, we want to calculate A1 is a A1 given by BI times probability of BI. Sum up this. This is the law of total probability. And because we roll a fair die to determine which urn we are choosing from. So it is 1/6 given by this one. And remember, the first urn, the ith urn always have I-1 red balls inside it. So we can use this term to calculate, which is a sum up from 1 to 6, I equal to 1 to 6 given by the I-1 divided by 5. And this is equal to 1/2. And also the probability of A intersection with A2. A1 intersection with A2. This is already calculated as A1 intersection with A2 given by BI times probability of BI. And for A1 times A1 intersection with A2, because as we see the process of how to choose in a die, how to choose in a bowl, is once we decide the urn, we repeatedly choosing balls from that urn. So once the urn is fixed, we do not consider any changing of the number of red balls inside it. And because it's with replacement, so every time the urn has the same number of balls and red balls. So it's 1. So we just give a square to say it's a 2-staged experiment. And from this formula, we calculate it is 11 divided by 30. And by the conditional probability formula, the probability of A2 given by A1 is the probability of A2 intersection with A1 divided by A1, which is 11 divided by 15. And for the second question, we're asking about compute BI given by A1. So this is a question that asks, the first ball you draw is a red ball. So what's the probability that we are choosing from the urn 1, urn 2, urn 3, or urn 5? So what's the urn we are choosing from? So obviously, this is a question of that examines your knowledge of Bayes' rule, because we don't know anything about BI given by A1, but we know A1 given by BI, so we can use the Bayes' rule as we sum up all of the cases of like A1 given by BI as in the denominator, and using just the BI as our numerator, and we find out is the denominator, which we already calculated in the previous case, in this case is 1/6 times the sum up of I from 1 to 6 given by I minus 1, times 5. And in the numerator, we are not summing those up, so we just give one case up, which is bi. So the result is I minus 1 divided by 15. So these are the two examples that illustrate how to use the Bayes rule. So to sum up, I think in this lecture we discussed the Bayes rule, the rule of total probability, and the conditional probability formula. Those are the three main things that is useful for the next lecture, for the future works. And we finally give a formal definition of what is a multi-stage experiment. So from now on, we are more focused on such complex cases with more than one stage. They are not all of the probability we meet in the future might not be simple as on one case and we are done. We are doing a chain of probability. And in such cases, we deal more with conditional probability and the use of Bayes rule and law of total probability.